followed by a well-known equation which is known as Henderson-Hasselbalch equation. After that, we will discuss the different types of acid-base titrations and the curves which are related to the acid-base titrations. So firstly, let's just sum up. What is a acid-base titration? When an acid and base are added, they neutralize one another and result into the formation of salt and water. So what happens is, for example, nitric acid is an acid. It neutralizes the base, which is potassium hydroxide, and results into the formation of salt and water. The acid donates proton and the base donates OH negative ions, which combine together to form water. Now, some common terms which are used in titration are titrant. Titrant is the solution which is taken in burette. Generally, the concentration of the solution which is taken in the burette is always fixed. It is precisely known to us, and hence the concentration of the solution taken in the burette is always fixed. It is known to us. It is the standard solution which we take. Next is the titrant or the analyte. Titrant or analyte is the solution whose concentration is to be estimated. So we take the titrant or the analyte whose concentration is to be estimated in the flask below, and that is known as titrant or analyte. And the next important term is equivalence point. It is a specific point at which acid neutralizes the base, or we can say that the base neutralizes the acid. At this point, the complete neutralization had taken place, and this is known as equivalence point. Equivalence point indicates that at that specific point, the number of protons and the hydroxyl groups present in the solution are equal. Next is the endpoint. Endpoint is the point where we will add extra ml, 0.1 ml, that is few drops, 1 or 2 drops of the solution, that is the titrant, from the burette, so that we can observe the color variation. Color change can be observed. This error is called additive error or titration error. So these are the 4 important terms. Firstly, titrant is the solution which we take in the burette whose concentration is known to us. So titrant, the solution which we take in the burette, is known as the standard solution. Its concentration is already precisely known to us. The next is the titrant. Titrant or analyte is the solution in the flask whose concentration is to be determined. And the equivalence point is the specific point during titration at which all the proton ions are neutralized by the hydroxyl ions, and this particular point is known as equivalence point. After that, we get endpoint. Endpoint is the point at which we have to add extra solution, that is 0.1 ml of the solution, so that color change can be observed. Okay, so this is the setup of titration. Firstly, we have a stand, and on the stand, a burette has been fixed. Below here, we have a conical flask, and as I told you that in the burette, we always take the solution whose concentration is already known to us. We take the standard solution, and in the conical flask, we take the solution whose concentration is to be determined. Okay, and while doing titration, certain points have to be kept in mind. Now we will be discussing the procedure of titration. Firstly, while performing titration, we should always clean our glassware. First of all, the burette should be cleaned, should be washed with water. It should be rinsed. Also, the tap of the burette should be rinsed with distilled water. Secondly, the burette should also be rinsed with the titrate solution. I will repeat it. The burette which we will be using, it should be firstly washed with water, and secondly it should be rinsed with distilled water, and then at the last it should be again rinsed with the titrant solution, so that no type of error occurs. And Another point which should be kept in the mind is we should check for the air bubbles. No air bubbles or leaks should be taking place during the titration. So we should check this before proceeding with the titration, that no bubbles or leaks are there in during the titration. So before starting the titration, we have to check the initial reading of the burette. We have to check the initial reading of the burette. The reading is taken in the way, in such a way that for the colorless solutions, we always consider the for the colorless solutions, we always consider the lower meniscus, and for the colored solutions, we consider the upper meniscus. So before starting the titration, the initial volume reading on the burette is noted down and recorded. And then we should start with the addition of solution, standard solution from the burette. The solution whose concentration is to be analyzed should be taken in the clean flask or beaker. It should be prepared in the flask or the beaker. And if the sample to be estimated is a solid, it should be dissolved in water, and the solution should be completely homogeneous. After preparing the sample in the flask, add indicator. After the addition of indicator, okay, now after the addition of indicator, we can start with the addition of the solution from the burette. And it should be always kept in mind that the addition of the solution from the burette should be done very slowly, and with the addition of few drops. We should not open the tap. It will always result in some type of error. Always the addition of burette is done drop by drop so that no error take place. So we use a burette to deliver a stream of titrant, that is the solution, standard solution, which is present in the burette. And the solution is added into the flask till the end point is observed, and end point is always indicated by the change in the color. So end point is always indicated by the change in the color. Whenever the change in the color is observed, end point is noted down. The volume which has been required for the endpoint to take place is again noted down by taking the reading from burette. It's very important to observe the endpoint. It is very important to observe the endpoint. Sometimes a temporary endpoint is observed. We have to make sure that a permanent endpoint is observed. The temporary endpoint generally disappears after a few seconds, so we should keep in mind that the endpoint should be permanent. And for that, to check that, we should keep our solution for a few seconds. If the color last long for a few seconds, then the endpoint is permanent and we can note down that particular point. And always use a wash bottle to rinse the sides of the flask, because there are chances of the solution to stick on the walls of the flask. So always use a wash bottle to rinse the sides of the flask and the tip of the burette, to be sure all the titrant is mixed in the flask. So always the tip of the burette should be inside the titrant so that no liquid gets stick on the wall of the flask. Make sure you know what the endpoint should like. The next very important point is that you should be sure how the endpoint is will look like. For phenolphthalein, the endpoint is the first permanent pale color. So for example, we consider phenolphthalein. The endpoint in case of phenolphthalein is a pale pink color. The pale pink color will last long for 10 to 20 minutes, and after that it will fade down. If a dark pink color is observed, if we reach at this particular point where the color of the solution gets darker than faint pink, it means that we have gone beyond the endpoint. We have passed the endpoint, and we have gone beyond the endpoint, and we need to perform our titration once again. So this was the procedure. So while performing titration, I will repeat it once again. All the glasswares which we use should be properly rinsed with water, and then it should be washed with water. It should be again rinsed with distilled water, and then rinsed with the titrant solution to be taken. We have to be sure that there are no bubbles or leaks during while performing the titration, and the tip of the burette should always be filled. The tip of the burette should always be filled, and we should not be having the solution beyond the calibration, beyond the point where there is no calibration. And while taking the reading, the meniscus should be taken in account. For the before starting the titration, first of all we should note down the initial volume reading, and we should be, and after the preparation of the solution whose concentration is to be known, indicator must be added into the flask. On the addition of standard solution from the burette, and after some point endpoint will be observed, and we should be clear with what the endpoint really looks like. For example, the color of phenolphthalein is faint pink. If the color goes to dark pink, it means that we have gone beyond the endpoint and we need to repeat the titration again. Okay, so after performing the reaction, we come to know how much of the solution from the burette has been used to completely neutralize the acid or base we have in the flask. So after performing the titration, after knowing the endpoint from the burette reading, we come to know what is the volume of the solution what is the volume of the solution we have taken for the complete neutralization of unknown sample of acid or base we have. For now, after knowing the volume of the sample which has been used for the neutralization, we use this equation which is known as M1V1 is equal to M2V2. M1V1, in place of M1V1, we can take molarity of an acid. A indicates here the molarity of the acid, volume of the acid, and B indicates the molarity of base, and VB denotes the volume of the base used. So this equation can be used to find out the concentration of the unknown sample we have in our flask. For example, we will consider two numericals. If we have 15.20 ml of 0.1 molar HCl solution, it is added to 30.60 ml of sodium hydroxide. What is the concentration of the base? So we can find out the concentration of the base by using equation Ma into Va is equal to Mb into Vb. Now, first of all, we know the concentration of the acid which we are using. We know the volume of the HCl which we have taken. Now, what we have to find out is the concentration of the base. We also know the volume of sodium hydroxide which has been taken into account. So by using this equation, we can simply apply the formula and put all the numerical values in the formula. Now, for in the place of Ma, we have written the concentration of HCl, that is 1.0 molar, and Va denotes the volume of acid which we have taken, that is 15.20, which is equal to Mb into Vb. Mb is the concentration of the base which we want to know, and Vb is the volume of the sodium hydroxide which we have taken. By applying the equation, we divide 30.60 here and we get the molarity, we get the concentration of the base, which comes out to be 0.49 molar. So this acid base titrations are very beneficial to find out the concentration of the unknown sample of acid or base. Simply by preparing a standard solution of a acid or a base, we can find out the concentration of any unknown sample, the concentration of acid content or base content in any unknown sample. One more numerical which we can solve by using this equation is, if we have 22.5 15 ml of 0.5 molar sodium hydroxide. If this solution is added to 16.50 ml of HCl, what will be the concentration of acid? Again, we can apply this equation, which is Ma into Va is equal to Mb into Vb. By applying this equation, we can come to know about the concentration of the acid. By using this equation, we can come to know that how much acid, what concentration of acid is required for the neutralization, how much concentration of HCl is required to neutralize 22.15 ml of 0.5 molar sodium hydroxide solution. So this was one more numerical which we can solve by using this equation. With the help of indicator, we exactly come to know the point at which the acid and base have completely neutralized with one another. From the endpoint, we can come to know what is the basic, what is the value of acid or base which has been used to neutralize the acid or base content in the unknown sample. So the key titration is a very simple procedure, but there is a key. The key to successful titration is patience. The titration should be performed with a lot of patience for the successful completion. Secondly, we should always use clean equipment. If we have equipment which contains impurities or some samples from our previous experiment, there are chances that error may take place. So first of all, the titration should always be performed with patience. If we do not perform titration with patience, there are always chances of error to take place. Second is always use clean equipment. Clean equipment should be used while performing titration because there will be chances of the error to take place. And read the meniscus very, very carefully. For example, for the colored solutions, we are always to use the upper meniscus, and for the colorless, we are always to use the lower meniscus. So we should read the meniscus reading very, very carefully. And after that, after we come to know about the endpoint, we can simply apply the equation, that is Ma into Va is equal to Mb into Vb, to calculate the concentration of the unknown solution. Now, what we will just once again go, what is acid base titration? Acid base titration is a procedure which is used for the quantitative chemical analysis. It is basically used for the quantitative chemical analysis to determine the concentration of either acid or a base. By acid base titration, we come to know about the acid or base content which is present in the unknown sample. So it is a quantitative measure, quantitative chemical analysis. The equivalence of acid base titration is the point at which there are equal amounts of hydronium ion and OH negative ions. So what is the equivalence point? Equivalence point is a specific point. It is a point at which we have equal amount of hydronium ion and OH negative ions. How are hydronium ion produced? Hydronium ions are produced when H positive proton ions react with water molecule to they form hydronium ion. So equivalence point is the specific point at which we have equal amounts of hydronium ion and hydroxyl ions. And the point after equivalence point, where we do addition of 0.1 ml to observe the pH change, is known as endpoint. So this is the reaction which takes place in acid base titration. Hydronium ion, or we can say that proton neutralizes hydroxyl ion, or we can say hydroxyl ion neutralizes the hydronium ion to form water, and this reaction is known as neutralization reaction. The end point of the titration, when we get the end point of the titration, it is indicated by the change in the color of the indicator. The indicator changes its color when the endpoint is observed, and hence we can note down the reading. The indicator should change color. Okay, as we know that the indicator, good indicator, should always change the color very sharply at the equivalence point. So the color of the indicator should change very, very sharply at that specific equivalence point. We should not be using an indicator which shows the pH, which shows the color variation over a range. We should be always using an indicator which shows us the color change sharply at the equivalence point. At the end point of the solution, all the acid has been neutralized by the acid, and the solution in the conical flask contains salt and water. What happens at the equivalence point? As we have seen that at the equivalence point, all the H positive ions have been neutralized in the water, and we have only salt and water left in our conical flask. Now, what were acid base indicators? Acid base indicators were weak organic acids or weak organic bases which dissociate slightly into the aqueous solutions to form ions. The indicators can change color because we have studied different theories for that. The indicators according to Oswald theory change color when because they have different color in the dissociated and undissociated form. According to benzoid theory, indicators have different color because they exist in two tautomeric forms, that is benzoid form or quinone form, and there are different colors in the two tautomeric forms, and hence the color variation is observed during the change in the pH. Now, acid-base titrations are of four types. The four types of acid-base titrations include the titration of strong acid with a strong base. Nextly, titration of a strong acid with a weak base. Third, titration of a weak acid with a strong base. And the last one is the titration of a weak acid with a weak base. Now, strong acid, we can use in the case of a titration of a strong acid with a strong base, we can use HCl, we can use nitric acid or any other strong acid like sulfuric acid. And in case of and strong base can be sodium hydroxide, potassium hydroxide, any strong base. For the second titration, that is titration of a strong acid with a weak base, we can use HCl, which is a strong acid, and weak base, that is ammonia. And in the third titration, we have a weak base, that is an acetic acid or any other weak. We can use any other weak acid, and we can titrate it with the strong base. The last one is titration of a weak acid with a weak base, in which we have both acid as well as base who are weak. The strength of acid and base are weak. So turn by turn, we will discuss all these reactions, and we will also discuss the graph of these reactions. So before that, we will discuss the most important equation, which is known as Henderson-Hasselbalch equation. This is very important equation. This equation is commonly used in chemistry and biology to determine the pH of the solution. So this equation it helps us to determine the pH of the solution. So in this equation, we can come to know about we can determine the pH of the solution. In this equation, we have a relationship between the pH or the pOH of the solution and the pKa or pKb of the solution and the concentration of the chemical species involved. We will study this equation, then it will be more clear to us. Basically, this equation is used to find out the pH of the solution. Using this equation, we can determine the pH of the solution. This equation is very important, and it is considered as the backbone of the acid base physiology. This is very important equation, and by using this equation, if we know the value of pKa or pKb and the concentration of the chemical species, we can easily find out the pH of the solution. And this equation is commonly used to determine the amount of acid and conjugate base which are required to prepare a buffer solution of desired pH. So according to In this theory, there are certain things which have to be kept in mind. This theory is based on Bronsted-Lowry concept of acid and bases. What is basically Bronsted-Lowry theory concept of acid or bases? According to Bronsted-Lowry theory of acid and bases, acid is any species which is capable of donating a proton, while a base is a substance which is capable of accepting a proton. So these Arrhenius theory and Bronsted-Lowry theory are different theories. They should not be confused. Arrhenius theory was, according to Arrhenius theory, an acid is a species which can donate a proton, while a base was a species which can donate hydroxyl ions. Whereas according to Bronsted-Lowry theory, acid is definitely a species which can donate a proton, while a base is a species which can accept a proton. So Arrhenius acid is a Lowry-Bronsted acid, but Arrhenius base is never a Lowry-Bronsted base. So these two things should be kept in mind. Acid according to Lowry concept and acid according to Arrhenius concept is definitely proton donor, a species which can donate proton, but Arrhenius base is something different. Arrhenius base is a species which can donate hydroxyl ions, whereas Bronsted-Lowry base is a species which can accept a proton. An acid, after losing a proton, it forms a conjugate base. An acid, after the loss of proton, it forms a conjugate base, that is A negative, and the protonated base exist as conjugate acid. So what happens when an acid and base reacts? Acid will lose a proton and it will be converted from Ha to A negative. The H positive part will be accepted by the base, and the base will turn into protonated base. It will exist in the form of BH positive. So these were the few assumptions which have to be kept in mind. So first of all, it should be kept in the mind what an acid and base is according to Bronsted-Lowry theory. Now this will be applied to determine the equation which is known as Henderson-Hasselbalch equation. So the derivation of this theory is based. Now we will start with the derivation. Now for the derivation, we have to first of all consider a weak acid and we have to consider a salt. First of all, we have taken a weak acid. Suppose that we represent it by Ha. We represent a weak acid by Ha. The acid will release H positive ions and A negative ion in the aqueous medium. So, and this is the equation for weak acid. Acid is nothing but it is going to release proton ions when it is dissolved in the aqueous medium. And then we have a base. We can consider a sorry. So this is we are considering a weak acid. Weak acid, example of weak acid is an acetic acid. Acetic acid gives H positive ions. After the loss of H positive ion, acetic acid forms acetate ion. So we have here acetic acid releasing proton and forming acetate ion. Secondly, we will take a salt. A salt dissociates into oppositely charged ions. We have taken a salt, that is Ba. It will dissociate itself into ions when dissolved in the aqueous medium, that is a cation portion and the anion portion, B plus and A negative. So here we have taken one example of salt, that is sodium acetate. Sodium acetate when dissolved in water will release acetate ion, that is CH3CO negative, and sodium ion, that is Na positive. Now we can see that we have taken acetic acid and we are taking sodium acetate. Both these ions dissociate themselves when dissolved in aqueous medium. Both the components, they release acetate ions, because both acetic acid as well as sodium acetate, they are releasing acetate ion, which is common in both the equations. So here common ion effect will take place. Now because of the common ionic effect, salt dissociates completely, whereas the weak acid dissociates partially. So what is going to happen? So since we have a weak acid, so its activity will be suppressed by the salt. the activity of the salt. So the weak acids activity will be suppressed by the salt because of the common ion effect. Same ion is being produced by two species. So the dissociation of acetic acid, since it is weak acid, will be suppressed because of the common ion effect. So here this is what is written here. Because of the common ion effect, salt is going to dissociate completely, whereas the weak acid will dissociate partially. The weak acid is going to dissociate only partially. So we can say that the A negative ion, that is the acetate ion, will mainly come from the salt and not from the weak acid. Why we will be getting the A negative, that is acetate ion, only from salt? Because of the common ion effect, the salt will definitely dissociate, but the weak acid will only dissociate partially because of the common ion effect. We will be applying equilibrium condition here. In the first equation, Ha gives H positive ions and A negative ions. So we will be applying the equilibrium here, the equation of equilibrium here. What we get is Ka, that is dissociation constant for an acid, is equal to concentration of the product divided by the concentration of the reactant. So the product here is the ions, are the ions, that is H positive and A negative, and divided by the concentration of the acid, that is Ha. Now we will be rearranging this equation. We will shift the H positive, concentration of H positive ions on one side, and we'll take all the terms on the other side. We will get equation number 2 on rearranging. Here we have only H positive, the concentration of H positive ions on one side, and the concentration of all other ions are kept on the another side. After rearrangement, we will be taking the negative log of this equation. After taking negative log of the whole equation, we will be taking the negative log on both the sides. So what is the equation which we get? That is equation number 3. We get minus log of H positive ions is equal to minus log of Ka into Ha divided by the concentration of A negative ions. So we will be applying some mathematical principles of log here. Log A minus B is equal to log A minus log B. So this is what we have applied here. So here we have log Ka minus log Ha divided by concentration of A negative ions. Now what is minus log of H positive? It is nothing, but it is equal to the pH of the solution. So minus log of H positive is nothing, but it is equal to the pH of the solution. As we have discussed in the previous lecture, minus log of Ka is known as pKa value, and the negative they will cancel out each other, so we will be getting a positive sign here, and we have plus log A negative divided by Ha. So this is the equation which is known as Henderson-Hasselbalch equation. This equation relates the pH of the solution with the pKa value of the acid. So what is this equation? This is pH is equal to pKa plus log of the concentration of ion, the concentration of the ion divided by the concentration of acid. So this is what we have written. This is A negative is the ion which we get from salt. So I have written here the concentration of the salt divided by the concentration of acid. We have discussed that due to common ion effect, the acetate ion, or we can say that A negative ion, will not be released by the weak acid, because of the common ion effect, the activity of the weak acid will be suppressed. So we will be getting the negative charged ions, that is the acetate ion, only from the salt. We will not be getting it from weak acid. So hence I have written in the place of A negative ion the concentration of the salt, because we know from this equation that 1 mole of salt is going to give us 1 mole of 1 mole of anionic portion. So from here we can also write in the place of the concentration of the A negative species, we can replace it by the concentration of the salt. BAA was nothing, but it was the concentration of the salt. So this is the equation, and this equation is very very beneficial. We normally use it to find out the pH of the solution. So we will just once revise this equation again. For studying this equation, we have taken weak acid and a salt. Weak acid will give H positive ions and A negative ion. We can say that weak acid is going to dissociate itself into Ha ions, that is proton ions, and the another and the negative portion of ions. And similarly, the salt also dissociates itself into oppositely charged species. That is. We have taken here a salt as Ba. It is going to give B positive ions and A negative ions. So we have got cations and anions from the salt. Now we have specifically taken here weak acid as acetic acid, and we have taken salt as sodium acetate. So what is going to happen when we will be dissolving it in the aqueous medium? Both acid and salt are going to dissociate into different ions. Since we get the same ion, we get the same anionic portion from acid and from the salt. A common ion effect is going to take place. The common ionic effect which is going to take place will suppress the activity of weak acid. Salt will completely dissociate, but acid, because of the common ion effect, the weak acid will not be able to release H positive ions, and it will not be able to form the negatively charged ion. So because of the common ion effect, the salt dissociates completely, whereas the weak acid is going to dissociate partially. This is common ion effect. When we get the same ion from two reactions, the activity of the weaker reagent is suppressed. So here is this, what is the same thing has been observed here. And at the last, we have applied equilibrium conditions here. From here, we will find out the value of Ka, that is equilibrium constant. For an acid, it is known as dissociation constant. For an acid will be nothing but the concentration of the ions divided by the concentration of the acid. On rearrangement, we will be taking the concentration of protons on one side and the concentration of all the remaining anions and acid on the other side. After that, negative, we will be taking the negative log on both the sides. And then minus log of H positive is nothing but it is the pH. Similarly, minus log Aa is nothing but it is the pKa value. Doing rearrangement here, we will get log A negative divided by log Ha. A negative is nothing but it is the anion which we get from the salt. So here in the place of A negative, I am writing down the concentration of the salt divided by the concentration of acid. So this is all about this equation. So next we will be discussing different types of acid-base titrations. So now we will be discussing the different types of acid-base titrations. As we have discussed, acid-base titrations are of four types. That is a reaction of a strong acid with a strong base. In this, we will be taking both strong acid and strong base. Secondly, we will be using a weak acid versus a strong base. We will take a weak acid and a strong base. And thirdly, we will take a strong acid versus weak base, and at the last we will be taking both weak base and weak acid. So this is the titration curve. This is basically the curve which we will be getting when we will be performing the titrations, which we will be discussing in the further section. Now, what is a titration curve? Titration curve is basically two-dimensional graph where we take on the x-axis, we take the volume of the titrant added. Volume of the titrant added, that is the solution which we is the standard solution which we have taken in the burette, which we are adding from up. That is the volume of the titrant added, and this is on the y-axis we deal with the pH of the analyte solution. pH of the analyte solution is a solution which we have down in the flask. So this is the graph which we will be plotting at different intervals. With the addition of titrant, we will be noting down the pH of the analyte solution. Now, in the titration curve, a curve normally in this shape is observed as we add the volume of the titrant. If the titrant is basic titrant, we are taking a base in the burette and we have an acid in the conical flask. So what is going to happen with the addition of the titrant? We can see that by the addition of the titrant, we will see that the pH of the analyte is increasing. So as we are adding the titrant, which is a base here, we can see that the pH is increasing, and with more and more addition of the base, which is acting as a titrant here, the pH will go on increasing, and once the maximum pH has been attained, we will be getting the continuous graph. There will be no more variation. Once the pH has reached the maximum extent, the pH is going to is not going to vary. It has already gone the max along beyond the maximum point. So this is the graph of titration. This is the graph which we usually observe during the titration. It is a two-dimensional graph. On the x-axis, we have the volume of the titrant which we are adding. That is the solution, standard solution which we have in the burette. And on the y-axis, we are taking the pH of the analyte solution. That is the solution whose concentration is to be determined. So as we are adding the basic titrant solution, we will observe that the pH is increasing slowly and slowly, and after a certain point the pH gets constant. So this type of graph we will be getting in three types of titrations, and we will discuss that one by one. So the first one is titration of a strong acid with a strong base. So what happens during titration of a strong acid and a strong base? We take both the analyte and the titrant to be having strong strength. So both the acid and base are going to be strong. So suppose strong acid can be any strong acid. For example, we are taking here HCl, and strong base can be any strong base like sodium hydroxide. So here we have taken strong acid as HCl and strong base as sodium hydroxide. Now suppose our analyte is hydrochloric acid. For just we can suppose that the sample whose concentration is to be determined, whose concentration we do not know, the sample whose concentration has to be estimated, we have taken that as HCl solution, and we take the sample whose concentration is to be estimated in the conical flask. So we have taken the HCl solution here below in the conical flask, and we have the titrant. We will be taking the titrant, so that is the base sodium hydroxide, and whose concentration is fixed. It will act as a standard solution. We have taken that in burette. So we will now what we will be doing, we will be adding drops of sodium hydroxide into the solution of HCl, and with the addition of sodium hydroxide drops, we will be noting down the pH of the analyte solution. So this is basically the graph which we will be getting. This is the HCl solution whose concentration has to be determined. We do not know the concentration of this HCl solution, and above here we have sodium hydroxide. Sodium hydroxide's concentration is already known to us. We will be adding down the sodium hydroxide into the solution of HCl, and we will determine the concentration of HCl. So what is going to happen when we perform this experiment of titration of a strong acid with a strong base? A curve like this is observed. So here we can see that as we are going to add sodium hydroxide, Since the on the here it is the same graph which I have just discussed in the previous slide. On the y-axis we have pH of the analyte solution. pH of the analyte solution is basically the pH of the HCl solution whose concentration is to be determined, and on the x-axis we are dealing with the volume of the titrant adding titrant which we are adding, that is the volume of the sodium hydroxide which we are adding. So what is going to happen as we are adding the sodium hydroxide in it, with the addition of sodium hydroxide we will be observing that the pH is going to increase as the as the sodium ions are being added into the conical flask. With the introduction of hydroxyl ions, the pH is going to go to the greater side and our solution will get basic, and hence the pH is going to increase. So we are adding sodium hydroxide solution here. So what happens here is, this is the point one. Here we add sodium. This is the first point. With the introduction of sodium hydroxide ions into the HCl solution, the pH is going to increase and point two is observed. At point two, we will observe that at point 2, we will observe that all the H positive ions have been neutralized by the OH negative ions. And this particular point is known as equivalence point. This is known as equivalence point. And after that, with the introduction of more hydroxyl ions, the pH of the solution will increase. First of all, the hydroxyl ions which we are adding into the conical flask, they are going to neutralize the H positive ions which are already present in the beaker. All the H positive ions which are already present in the beaker will be neutralized by the sodium hydroxide which we are adding from the burette. So this is the curve which we will be getting here. After some time, the pH is going to remain. The pH is going to change abruptly. So we can observe that the pH will change abruptly. This at a specific point, the pH is going to abruptly change. At this particular point, all the H positive ions have been neutralized by the OH negative ions which we are adding from the burette. So this particular point is known as the equivalence point. At this particular point, we have equal number of H positive ions and equal number of hydroxyl ions. Beyond this point, after this point, we will observe that with the more introduction of hydroxyl group, there will be now the number of hydroxyl ion will increase the number of proton ions which are present in the solution, and hence our solution will become now basic in nature. So this is the curve. We will discuss this curve in some more detail by considering 4 points of these curves, that is point number 1 here, point number 2, point number 3 and point number 4. So the first case here we will be discussing first is the point number 1 in strong acid and in case of strong acid and a strong base. This particular point 1 is a point at which we have not added any sodium hydroxide solution to it. At point 1, we have not added, no sodium hydroxide has been added. So the pH of the solution will be low. Since we are taking HCl solution, our analyte is HCl solution. Since we have not added any sodium hydroxide at this particular point, so the pH is definitely going to be low because the solution is HCl solution, it is acidic. So at point 1, since no sodium hydroxide has been added, so the pH of the analyte is going to be low. It predominantly contains hydronium ions from the dissociation of HCl. At this particular point where we have not added any sodium hydroxide, we will be having only hydronium ions which we have got after the release of H positive ions from the HCl solutions. What do what does HCl acid do? HCl acid dissociates into H positive ion and Cl negative ions. The H positive ions are going to combine with the water molecule to form hydronium ion and Cl negative ions. So this is the concentration of ions which we get at point number 1. We have hydronium ions and Cl negative ion. After now, as sodium hydroxide is added dropwise. As we are going to add sodium hydroxide in the solution dropwise, what is going to happen? The OH negative ions of the sodium hydroxide are going to neutralize the hydronium ions which we have, which are present in the solution from the HCl portion. So as sodium hydroxide is added dropwise, hydronium ion is slowly hydronium ion slowly starts getting consumed. Now the hydronium ion, on the introduction of OH negative ions from the burette, they will be consumed by the OH negative ions which have been produced by the dissociation of sodium hydroxide. Analyte will be still acidic because we have not added sufficient number of OH negative ions which are present. We have not added sufficient number of OH negative ions which are required for the complete neutralization of proton ions for the protons. So still the concentration, the pH of the medium will be acidic. Now, in the point number 2, this was the first point where we have not added any sodium hydroxide solution. Now, next is point number 2. So, at point number 2, we have added sodium hydroxide ion. This is the pH. What happens at point number 2? This is the pH recorded at the time just before complete neutralization takes place. So second point is a point at which complete neutralization just is a point just before the complete neutralization has taken place. So this second point is a point at just before where complete neutralization has taken place. Now point number 3. Here, this is known as equivalence point. This is a point which is known as equivalence point. It is the point at which the number of moles of sodium hydroxide which we have added from the burette are equal to the moles of HCl which we have in the analyte solution. At this point, hydronium ions are completely neutralized by the OH negative ions which we have added from outside. The solution at point number 3 has only salt, that is NaCl, and water, and hence the pH of the solution is neutral, that is it is 7. So what happens at point number 3? All the H positive ions which have been released by the HCl solution have been neutralized with the base ions which we are adding from outside. So at this point we have equal number of H positive ions and equal number of hydroxyl ions, H negative ions. So they will completely neutralize one another, and the overall pH of the solution will be neutral, that is the pH will be 7. So what happens here is HCl, which we have taken as an analyte, it has reacted with the base, and whenever acid and base they react, they always form salt and water. So with the reaction of acid and base we get salt and water. So at point number 3 we have no we have only NaCl and water present with us. Okay, so this is the point number 3. So what the last point is point number 4. What happens at point number 4? On the addition of more sodium hydroxide, pH will now start increasing. We have already consumed those OH negative ions, the amount of OH negative ions which were required for the neutralization of H positive proton ions present in the HCl solution. Now the hydroxyl ions which we are using, they are extra and they are just going to increase the pH of the solution. Now with more introduction of OH negative ions, the pH of the solution will change into basic. It will be basic now, because the HCl which was present in our flask has already been completely neutralized. It has already been completely neutralized, and now the excess OH negative ions are present in the solution. Because of the excess OH negative ions which are present in the solution, our solution is going to become basic in nature. So this is the point after equivalence point. At point number 4, sodium hydroxide ion, after the equivalence point they are going to give sodium ions and OH negative ions. So these are the 4 points. What are the 4 points of a strong? What are the 4 points which are observed during titration of a strong acid and a strong base? The first point was the point where we have not added any sodium hydroxide. At this point, only hydronium ion was present and the pH of the medium was acidic. The pH was low. It was the solution was acidic. Okay, and with the introduction of hydroxyl ions, as we are adding base, our curve is proceeding here. It is proceeding towards the higher pH, and a specific second point is a point at which is a second point is a particular point at which it is a point just before the equivalence point. It is just before the equivalence point. Point 3 is a point where we have is a specific point at which all the proton ions have been completely neutralized by the hydroxyl ions. So this is the point number 3. After point 3, we have point 4. This is a point at which we have extra base ions. So after this, the solution becomes basic in nature. So this is the graph. Now we will be discussing these graphs with some numerical values. So we have 4 points when no sodium hydroxide has been added. Second point is a point just before the equivalence point. Third point is sharp equivalence point at which we have equal number of proton ions and hydroxyl ions. And point number 4 is the point at which we have added extra sodium hydroxide and we have only hydroxyl ions present in the solution with salt and water. So we will explain this more with the help of some numerical values. Let us consider an example of titration of a strong acid, that is HCl, and a strong base, that is sodium hydroxide. So we consider this reaction that is between HCl and sodium hydroxide. Reaction of HCl and sodium hydroxide gives us salt and water. The HCl will release H positive ions and Cl negative ions, whereas sodium hydroxide is going to release Na positive ions and OH negative ions. OH negative ions from the base portion are going to neutralize the H positive ions from the HCl. H positive ions and OH negative ions, they combine to form water, whereas the remaining Na positive ions and the Cl negative ions from the HCl combine to form salt. So now we will be considering the different points with some numerical values. We suppose that we are adding 50 ml of 0.1 normal sodium hydroxide. Suppose we are dealing with 50 ml of 0.1 normal sodium hydroxide solution, and we have 50 ml of 0.1 normal HCl solution. So here we have taken 50 ml of sodium hydroxide and 50 ml of HCl solution. The concentration of both acid and base is exactly the same, that is 0.1 normal sodium hydroxide and 0.1 normal HCl solution. The various pH changes at different stages. We will be now studying the various pH changes at the different stages of the addition. So the first one is pH before the addition of sodium hydroxide. The first point was the point at which we have not added any sodium hydroxide solution. At that point, we had only hydronium ions. So we have 50 ml of 0.1 normal HCl solution. So the concentration of HCl is 0.1 normal. So how many proton ions, or we can say how many hydronium H positive ions will be present in the solution? That will be exactly equal to 0.1 gram ions per liter. So this gram ions per liter is nothing but the units of normality. So for 0.1 normal HCl solution, we have 0.1 gram ions per liter. We have 0.1 gram ions per liter H positive ions. So this is the concentration of this is the concentration of H positive ions. At point number 1, we do not have any other ion since we have not introduced sodium hydroxide solution in it. At point number 1, we have only HCl solution. So we have only H positive ions in our medium. So the concentration of H positive ion is exactly the same as the at concentration of HCl, because HCl is directly going to dissociate into H positive ions and Cl negative ions. So the concentration of H positive ions is 0.1, or we can also write it as 10 the raised to power minus 1. So this is the concentration of H positive ions in our medium. When we take log on both the sides, now we will be taking the log on both sides because we want to find the pH. So taking log on both sides, we get log H positive is equal to log 10 minus 10 the power minus 1. So after that, definitely we will be taking negative sign. When we will be taking negative sign on both the sides, so when we will be taking negative sign on both the sides, we will get here on the left hand side, we will be getting the pH. Okay, and the pH will approximately come out to be less than 7 because we have only HCl ions here, and our medium contains only H positive ions, and hence our medium is acidic in nature. What happens at point number 2? The point number 2 is a specific point at which equivalence point is just about to start. So what was point number 2? At point number 2, we have, it is a point where equivalence point is just about to reach. So what happens? We will consider this numerically. The pH, we will find out the pH at point number 2. pH after addition of 10 ml of sodium hydroxide. For example, we in this equation, in this here we have taken 50 ml of 0.1 normal HCl. In that we have added 10 ml of sodium hydroxide ions. So we have added 10 ml of sodium hydroxide. So what is going to happen? So we can find out the pH of the solution by using this equation. By using this equation, what this equation says that normality of HCl, that is known to us, multiplied by total volume of the solution which we have, is equal to normality of sodium hydroxide multiplied by the volume of sodium hydroxide which is unreacted. So this is the equation which we will be using for finding out the pH of the solution. This, according to this equation, a concentration of HCl multiplied by the total volume of the sample which we have in the conical flask is equal to the concentration of the base multiplied by the volume of the sodium hydroxide which is unreacted. So just by simplification, what we get, we will be taking the concentration of HCl on one side and all other quantities on the other side. Since the concentration of sodium hydroxide, we have already fixed that is 0.1, and the volume of sodium hydroxide which is unreacted is 40, because we have taken the total volume to be 50. Since only 10 ml have been added, so the unreacted sodium hydroxide will be 50 minus 10, that is 40, divided by the total volume. Now the total volume is, what will be the total volume? We have already 50 ml of HCl in our conical flask, and we have added 10 ml of sodium hydroxide. So 50 plus 10 ml will be 60. So we divide the whole equation by 50, because here we have total volume, so we have to divide it by the total volume of the sample. So the total volume of the sample is 60. So on simplification, we get the normality of HCl, that is 0.0667 normal. So what is the normality of HCl solution? That comes out to be 0.0667 normal, and this is the normality. So we also know that if the normality of HCl solution is 0.0667, it means it has 0.667 grams per gram ions per liter H proton ions. Okay, so we, from this equation, we have already calculated the concentration of proton ions. From the concentration of proton ions, we can calculate the pH. How can we come to the pH? By the concentration of proton ions. First of all, we will be taking log. By taking log, on both the sides, log proton, log the concentration of proton ions is equal to log concentration of this term. After that, we will be taking negative on both the sides. We will be taking negative log on both the sides. After simplification, left side minus log of H positive ions is nothing, but it is the pH. So left hand side, on the left hand side, we have pH, and the pH comes out to be 1.18. So this is the pH of the solution after addition of 10 ml of sodium hydroxide. How we are calculating this? We have calculated this by using the equation concentration of HCl solution into the total volume is equal to the concentration of sodium hydroxide multiplied by the volume of sodium hydroxide which is unreacted. Since we have added only 10 ml of sodium hydroxide, so the unreacted sodium hydroxide will be, for total volume, that is 50 minus 10, uh, 50 minus 10, that is 40. And what is the total volume at this particular stage? It will be 50 ml HCl plus 10 ml of sodium hydroxide which we have added. 50 plus 10 comes out to be 60. So by this equation we come to know about the normality of HCl. From the normality we have calculated the number of hydronium ions from the concentration of hydronium ions. By taking a negative log, we have calculated the pH of the solution at that particular point. Now, third point, the third case we are considering, the third case is the pH after addition of 20 ml. So we are going to apply the same equation again. Now we will be finding out the pH after addition of 20 ml of sodium hydroxide solution. Again, we are going to use the same equation, that is the concentration of HCl solution into the total volume of the solution is equal to the concentration of sodium hydroxide into the volume of unreacted sodium hydroxide. It is multiplied by volume of unreacted sodium hydroxide. So the normality of the equation, normality of the sodium hydroxide solution is known to us, that is 0.1. The volume of sodium hydroxide solution which is unreacted will be 30 here, because the total concentration was 50. Total volume was 50, minus 20, that comes out to be 30, and the total volume will be 50 ml of HCl plus 20 ml of HCl, that is 70. So from this again we have calculated the normality of HCl solution at interval where we have added 20 ml of sodium hydroxide in the solution. So by again now, since the normality of the HCl solution here is 0.0428 normal, from here we can calculate the number of proton H positive ions, that will be same, that is the number of proton ions H positive ions is 0.0428. Okay, after taking the negative log, we will be getting pH, and on calculation we will get the pH to be 1.37. We can observe that on the introduction of sodium hydroxide solution, the pH is increasing. It is shifting towards higher pH because of the addition of sodium hydroxide ions. Now, the fourth case is the point after the addition of 50 ml of sodium hydroxide. What is going to happen after, what will be the pH of the solution when we have added 50 ml of sodium hydroxide? Since we had 50 ml of HCl solution in our conical flask, and for the complete neutralization of 50 ml of 0.1 normal HCl solution, 50 ml of sodium hydroxide solution of 0.1 normal concentration was required. So what is going to happen at this specific point? All the H positive ions which were produced by HCl have been neutralized by the OH negative ions, OH negative ions which have been produced by sodium hydroxide. So at this particular ions, the number of H positive ion and the number of hydroxyl ions is going to be the same, and hence the medium and hence our solution will be neutral. And at neutral we have the pH 7. So the pH of the solution will be 7, and in this case, because we have equal number of H positive ion and OH negative ions. Now what will happen after the addition of more sodium hydroxide ions? 50 ml of sodium hydroxide ions, as we have seen from the equation, 1 mole of HCl is going to react with 1 mole of sodium hydroxide. Now for 50 ml, we have already, for 50 ml HCl, 50 ml of sodium hydroxide of same concentration have been used. Now what will happen? 50 ml was required to react with 50 ml of sodium hydroxide of the same concentration. Now, after the further addition of sodium hydroxide, what is going to happen? There are no more proton ions whose neutralization is to take place. So, after the further addition of more sodium hydroxide ions, what is going to happen? Now, our solution is going to shift towards the basic side. The pH is going to increase towards, it is going to increase beyond 7, and the solution will be basic in this situation. So what is going to happen here? The Since all the H positive ions have been neutralized, now we will be having the OH negative ions. The OH negative ions, the OH negative ions will make the solution basic now. So let us calculate the concentration now. The concentration of sodium hydroxide ions is equal to 0.1. Since we have added extra 0.1 ml, so that we have taken here 0.1 ml multiplied by the concentration of sodium hydroxide. The concentration of sodium hydroxide was 0.1 normal, divided by 100. 100 is the total concentration of the solution. Here we are not writing it as 100.1 because it makes no difference in the total numerical value, so we are just taking it as 100 here. We have applied the same equation which we have used here also, and from here, in from this equation we come to know about the concentration of sodium hydroxide ions. So we come to know about the concentration, pH of the solution. Now on solving, we get the value comes out to be 10 the raised to power minus 4. This is the concentration of the sodium hydroxide ions. Since 1 mole of sodium hydroxide is going to give 1 mole of hydroxyl ions, so 10 the raised to power minus 4 sodium hydroxide ions are going to give the same number of OH negative ions. Now from since we know the concentration of OH negative ions, we will be applying the equation according to which the concentration of proton ions multiplied by the concentration of hydroxyl ions is equal to 10 the raised to power minus 14. This is a well-known equation according to which the concentration of H positive ion and the concentration of hydroxyl ions is equal to 10 the raised to power minus 4. Since we know the concentration of OH negative ions, we will substitute the value of concentration of OH negative ions here, and we will be calculating the concentration of H positive ions. So the concentration of hydroxyl ions is 10 the raised to power minus 4, and from here we will be calculating the concentration of H positive ions. The concentration of H positive ion comes out to be 10 the raised to power minus 10. Now, since we know the concentration of H positive ions, we will be taking the negative log. By taking negative log of H positive ions, we will be getting pH on the left hand side, and the value here comes out to be 10. So after the addition of extra 0.1 ml of sodium hydroxide, beyond the equivalence point, the pH will directly change to 10. So this is the sudden rise in the pH. This sudden rise in the pH is known as inflection. So we can observe that earlier the solution uh, was having pH 7. On the addition of 50 ml of sodium hydroxide solution, the pH of the solution was exactly 7. After the addition of 0.1 ml of sodium hydroxide, with only addition of 0.1 ml sodium hydroxide solution, the pH has directly gone from 7 to 10. This sharp rise, sudden rise, is known as inflection. The sudden rise in the pH is called inflection. Okay, so this is the neutralization curve, which is observed for strong acid and strong bases. So here in on the x-axis we have the ml of titrant, that is the solution which we are adding from the burette, and on the y-axis we have On the y-axis we have the pH. On the addition of titrant, that is here we are dealing with basic titrant, the pH we can observe that it for earlier it was increasing slowly, and after the point of equivalence there is a sudden rise in the pH. Okay, so after the point of equivalence we observe, we see a sudden rise in the pH. The sudden rise in the pH is known as the point of inflection. So this point, the midpoint at which the pH increases abruptly, is known as equivalence point. Here we have equivalence point. So these are the different indicators which we can use for the acid base titrations. Methyl orange, it shows color variation from this pH, that is from 3.5 to 4.5 pH. And bromothiamol blue, it shows color variation from color variation at the pH 6 to 7.5 pH. And phenolphthalein shows color variation at pH interval 8.3 to 10. So this particular point at which sudden pH change is observed is known as point of inflection. This from, we can say that 4.5 to 9.5, where the sudden change in pH is observed, is known as point of inflection. This is particular point where inflection is observed, and these indicators which are sensitive at this particular inflection interval can be used as indicator in the titration of acid and base, strong acid and strong base. So we will sum up this theory of strong acid and strong base. The results which are provided in the table show that when one normal solution of strong acid is titrated with, here we are taking we always take the same concentration of acid and base. When one normal solution of a strong acid is titrated with one normal solution of a strong base, the inflection in the pH, the sudden rise in the pH is generally observed from 3.3 to 10.7 pH. That is the units are basically, that is 7.4 units. Any indicator which shows a color change between this pH range can be used as indicator for that particular titration. When we are using zero point 0.1 normal solution of strong acid, we titrate it with zero point 0.1 normal solution of a strong base. The period of inflection reduces to 4.3 to 9.7. That is, the inflection period is only 5.4 now. Only those indicators for the titration of zero point 0.1 normal solution of a strong acid with that of zero point 0.1 normal strong base, we can use only those indicators which show color variation at this particular small interval. By decreasing the concentration more further, for example, now here we will be decreasing the concentration more by 1/10 time. If we have 0.01 normal or strong acid, we titrate it with 0.01 normal solution of a strong base. The inflection is further reduced to pH 5.3 to 8.7 only. That is, the inflection will be observed only between the pH range difference of only 3.4 units. So we have to select the indicator. Now the choice of indicator will be very limited, and since methyl orange is not sensitive at this pH, it is sensitive at only lower pH. So for the estimation of 0.01 normal 0.01 normal concentration of the solution, methyl orange cannot be used. Since we have seen that methyl orange was only effective at lower pH, and bromothiamol is effective, shows pH variation, color variation at the pH 6 to 7.5, and phenolphthalein shows color variation at higher pH, at basic pH. So by decreasing the concentration, the inflection reduces, the period of inflection reduces, and hence the choice of indicator is also limited. Now these are some more findings. These findings, these are some more findings. Here we are just decreasing down the concentration of the solution. First of all, in the lower curve we have 0.1 molar, in the upper curve we have 0.01 molar, in the next the curve we have the concentration 0.001 molar, and in the upper curve we have the concentration 0.001 molar. So we can observe that as the concentration is decreasing, the point of inflection, this how we observe the point of inflection, it is generally indicated by this line, the line at which the sharp pH is observed. For 0.1 molar solution, the inflection period is too large. It is basically from 3 to 11.5, whereas if the concentration is decreased to 0.01 molar, if the concentration is decreased to 0.01 molar, the inflection is reduced. The inflection period has been reduced. And if we are further decreasing the concentration of the solution, the inflection period is reduced to more extent. And the last concentration where we have the solution of very low concentration, the inflection period is very small. So hence we can say that as the concentration is decreasing, as we are decreasing down the concentration, the inflection period is decreasing, and hence the inflection pH is decreasing. The point at which the color variation is observed is decreasing, and hence the choice of indicators also decreases as the concentration of the solution is decreasing. And the next type of titration is titration of a weak acid with a strong base. So first of all, we have discussed the titration of a strong acid with a strong base. Now we will be taking a weak acid instead of a strong base. So in the place of HCl, we will be taking a weak acid that can be acetic acid. So now we will discuss the titration of acetic acid and sodium hydroxide. Instead of a strong acid, we are using a weak acid here, that is acetic acid. So now our analyte is the substance whose concentration is to be determined. Analyte has been taken, that is acetic acid has been taken in the conical flask, and the titrant is sodium hydroxide. The titrant is sodium hydroxide, it is taken in the burette, and again we will be plotting the curve. When we perform this experiment, so we will be observing that as the pH, as the volume of the titrant is added, more and more titrant is added in the mixture, added in the solution, the pH is increasing. So as we can observe that as the volume of the sodium hydroxide ions is increasing, as we are adding more and more sodium hydroxide solution into our analyte mixture, analyte solution, the pH is again increasing. There is a difference between these two curves which we will be discussing in the later on slides. So this is the shape of the curve is exactly the same as we have seen previously in the case of titration of a strong acid with a strong base. The difference here is that in the case of titration of a weak acid with a strong base, the point of inflection, the inflection period is again small, and we will discuss it further in the next slide. So again, now what we have done here, we will be taking a weak acid, that is acetic acid, as an analyte in the conical flask, and we are adding sodium hydroxide solution. When we plot the graph, again we get the graph in that same shape, and we will be observing the 4 points. We will observe the 4 points in the graph turn by turn. This particular point at which abrupt change, we observe a sharp change in the pH has taken place. The midpoint at which the sharp pH has taken place is known as the point of equivalence or equivalence point. We will again discuss all the points turn by turn. So point 1 was the point at which we have not added any sodium hydroxide solution. So the point 1 is a point at which we have not added any sodium hydroxide solution. So the pH of the medium, the pH of the solution, that is analyte, will be low here because we have not added any sodium hydroxide solution into it. So we will be having only acetic acid. Acetic acid dissociates itself partially because it is a weak acid. It will only dissociate itself partially into acetate ion and hydronium ion. The H positive ion which has been lost from the acetic acid combines with water to form hydronium ion. So at point number 1, we will be having only acetate ion and hydronium ion. So point 1, when no sodium hydroxide ion is added, the pH of the solution is low because of the presence of only hydronium ions. But the difference between the two graphs is that in the previous graph we were dealing with strong acid. Here we are dealing with weak acid. So the strong acid dissociates itself completely into H positive ions, whereas acetic acid, being a weak acid, it will only partially dissociate itself into H positive ion and acetate ion. So since acetic acid has not completely dissociated itself into H positive ions, so we can observe that there will be lesser number of H positive ions, and because of the lesser number of H positive ions, you will be having lesser number of hydronium ions. Since the concentration of H positive ions or hydronium ions is low as compared to the solution in which previously which we have taken HCl solution, so we can say since the number of H positive ions is less, so the pH of the analyte solution will be more. Since we have less number of H positive ions, means our solution is not that acidic, and hence the pH will be little higher than that of the previous titration curve. Okay, so here in the previous titration curve, the point number 1 was present little below because in that we had used analyte as HCl. HCl was used as analyte. Since HCl is a strong acid, it will dissociate itself completely into H positive ions. Hence, the medium was more acidic and hence the pH of the solution was low. Whereas in case of acetic acid, it is a weak acid, it only partially dissociates itself into H positive ions and acetate ions. So the number of H positive ions in the solution will be less as compared to that solution which has HCl. So we can say that now in case of acetic ion, the solution containing the solution containing acetic acid, the pH is going to be slightly more. Okay, now this was the point number 1. Now we will after point number 1, we will be adding sodium hydroxide dropwise. As we will be adding sodium hydroxide dropwise, we will observe that the hydronium ions which have been produced by the dissociation of acetic acid are getting slowly consumed, are getting slowly neutralized by the OH negative ions which we are adding from the burette, that is sodium hydroxide which we are adding from the burette. So slowly with the addition of drops, the hydronium ions in the analyte solution will be neutralized, will be consumed by the OH negative ions which are produced by the dissociation of sodium hydroxide solution. Since since we are adding, still the equivalence point has not been observed. So equivalence point has not been observed till this stage. So we can say that our medium will be still acidic because the number of hydronium ions is more as compared to the number of OH negative ions. So this is point number 2. This is as we have discussed in the previous curve of strong acid with strong base. pH point number 2 is a point recorded at a time just before the complete neutralization takes place. So point number 2 is a point which is recorded at a time just before the complete neutralization has taken place. So this is a point. This is point number 2. Now the next is point 3. At point, what is point 3? Point 3 is a specific point at which all the hydronium ions which were present in our analyte solution have been neutralized by the OH negative ions, which we have added from the burette. So at point number 3, complete neutralization has taken place. This is the equivalent. So this point is known as equivalence point. Why is this known as equivalence point? Because the number of H positive ions which have been produced by the acetic acid are completely equal to the number of OH negative ions present in the solution. So point number 3, this is the equivalence point. Okay, this is basically halfway. This is the middle of the steep curve. At this point, the moles of sodium hydroxide added is equal to the moles of acetic acid which were present in the analyte. The hydronium ions are completely neutralized. The hydronium ions which were produced by acetic acid have been completely neutralized by the OH negative ions. The solution contains, now at the equivalence point, since there are equal number of H positive ions and OH negative ions, they have completely neutralized each other to form water. So at equivalence point, that is point number 3, we will be having only water molecule and we will be having only salt. Salt is formed by the association of Na positive ion and the acetate ion which have been produced after the dissociation of acetic acid. So the titration of so one more important observation which we have to keep in mind. So the curve is exactly similar to us. The curve of titration of a strong acid and a strong base is in the same shape as that of the titration of a weak acid with the strong base. So what is the difference? So let us pause here for a second and find out what is the difference here as compared to the case number 1. In the case of weak acid versus strong base, the pH is not neutral at the equivalence point. One very important difference between the titration of a strong acid and a strong base compared to that of the titration of a weak acid with a strong base is that at the equivalence point, the pH is not neutral. In the case of strong acid and the strong base, the pH was neutral, but now in the case of the titration of a weak acid and the strong base, the pH at the equivalence point is not neutral. It is slightly, the solution is basic at the equivalence point. What is the reason? Why is it so? As we have seen, at point 3, we have salt, that is sodium acetate and water. So sodium acetate salt which has been produced at the equivalence point will not remain as such. It will dissociate itself into Na positive ions and acetate ions. I will repeat it. The at point 3, the salt which we have produced, that is the sodium acetate salt, is not going to remain as such. It is going to dissociate into Na positive ions and acetate ions due to the presence. Now this acetate ion is going to further react with the water molecule. It is going to react with the further water molecule to it will attract H positive. The positive part of the water will be attracted towards the acetate ion and it will form complete molecule of acetic acid, whereas the OH negative ions which will be produced will be remaining in the solution as such. Because of these OH negative ions which have been produced in the solution, the pH of the solution becomes basic, although it should have been neutral, because the number of H positive ions which were produced by acetic acid is equal to the number of OH negative ions which have been produced, which have been transferred from the burette. But still, the at the point of equivalence, it is observed that the pH is not 7. The pH is not neutral in case of titration of a weak acid with a strong base. The reason behind this was that at equivalence point, the solution contains sodium acetate salt, and the sodium acetate salt dissociates itself into acetate ions and sodium ions. So this solution the salt, when it dissociates itself into acetate ions and sodium ions, the acetate ions are going to further react with water. They will accept H positive part of the water. They will combine with the H positive part of the water, but still the H negative portion of the water will remain as such, and it will make the solution basic. So this was a difference between the curve of a strong acid, this was the difference between the titration curve of a strong acid with a strong base and titration of a weak acid with the strong base. At equivalence point specifically, we do not have neutral pH in case of the titration of a weak acid with a strong base, whereas in case of titration of a strong acid with a strong base, the pH of the solution was neutral. Now, one more point, that was point number 4. We will be discussing point number 4. Point number 4 is the point beyond the equivalence point. When we add more sodium hydroxide solution beyond the equivalence point, we get point number 4. What happens beyond this equivalence point? When sodium hydroxide is added in excess, the curve is identical to HCl, sodium hydroxide solution. After that point, the graph is exactly the same as that of titration of strong acid with a strong base. The graph is exactly the same. It will be, the pH will be increasing when we will be adding further sodium hydroxide solution. It will be exactly same as that of titration curve of strong acid with a strong base. And so this let us compare the two graphs of strong acid strong base and with that of titration of a weak acid with a strong base. So first of all, as I told you that since when we are doing titration with a strong acid and a strong base, we are using HCl. HCl completely dissociates itself into H positive ions. Hence, the pH in the beginning is low. Whereas when we perform titration of a weak acid with a strong base, we are using acetic acid. Acetic acid do not, when we are doing the, when we perform the titration of weak acid with a strong base, the curve starts from higher pH. The curve starts from higher pH because the acetic acid which we have used do not dissociate itself completely into H positive ions, and hence the pH is more as compared to the pH. It is more as compared to the pH in case of strong acid versus strong base titration. This is the difference in the beginning, and also we have observed that at in the case of strong acid and strong base, the equivalence point, that is the midway of this steep curve, is neutral pH. It is neutral pH, whereas in case of in case of titration of a weak acid with a strong base, the curve, the equivalence point will not be neutral, it will be basic, it will be little basic in nature. And this is the curve. After the equivalence point, the graph is exactly the same in both the cases. Third type of titration is titration of a strong acid with a weak base. Now here we have taken a strong acid instead of a weak acid which we have taken previously, but now our base is weak. So here strong acid, we will be taking HCl as a strong acid, and ammonia will behave as weak base. Similarly, we will be performing the titration, and on the addition of titrant, with the addition of the titrant, the pH of the analyte solution will be recorded. Again, it has been observed that with the addition of more and more titrant, volume of titrant, the pH is increasing and the shape of the curve is also the same. Now we will okay, so suppose our analyte, now here we are taking analyte Analyte, the substance whose concentration is to be determined, is HCl, and the titrant here is ammonia. So ammonia act as a titrant here. With the addition of ammonia ions in the HCl solution, we are going to plot the curve. On the y-axis, we have the pH of the analyte solution, and on the x-axis, we have the volume of the titrant added. And this shape of titration curve is observed. Now we will study this titration curve in more detail. So again, we will be discussing the 4 points in the titration curve. The first point, we will start with the first point. The first point is a point at which we have not added any base from the burette. We have not added any ammonia ions in the ammonia drops in the HCl solution. So since we have not added any drops of ammonia in the solution, our solution is completely acidic in nature. We have only H positive ions and Cl negative ions which have been formed by the dissociation of HCl. So at point 1, we have not added, no ammonia has been added yet. So the pH of the analyte is low because we have only HCl solution here. At point 1, we have only HCl solution. HCl is going to break into H positive ions. H positive ions are going to form hydronium ions, and Cl negative ions are produced. After point 1, we will be adding drops of ammonia. As ammonia is added dropwise, the hydronium ions which have been produced by the dissociation of HCl will be neutralized, will be consumed by ammonia, which we are adding from the burette. Here, since we are using a weak base, so the neutralization will not be that fast as it was in the case of titration of a weak acid with a strong base, because always a strong acid has more strength of neutralizing. It neutralizes the acid with greater strength, whereas we are using weak base here, so the neutralization will take place, but it will take place slowly. Analyte is since at point number 2, since we have not added enough ammonia molecules in the solution, we have not added equal number of ammonia molecules into the solution. Since the number of ammonia molecules are not equal to the number of H positive ions in the conical flask present, so our solution will be acidic. In this case. As ammonia is added dropwise, hydronium ion is slowly starts being consumed by the hydronium ion is slowly consumed by the ammonia molecules. So what happens when we add a molecule, when we are adding drops of ammonia? Ammonia reacts with hydronium ion. Ammonia accepts H positive, accepts proton from the hydronium ion. So when it accepts H positive proton ion from the hydronium ion, it forms ammonium ion, and water molecule is produced. So what happens here, since ammonia contains lone pair of electrons, it has capacity of attracting H positive ions towards itself. So ammonia, because of the presence of lone pair of electrons, because of the electron density present on nitrogen, it is going to accept H positive, ions from the hydronium ion, and ammonia will be changed into ammonium ion. So this is the reaction which will take place. So at point 2, this is the pH recorded just before the complete neutralization takes place. So at point number 2, it is a specific point at just before complete neutralization takes place. So this is a point. And next is point 3. Point 3 is the equivalence point. Is halfway. It is the midpoint of the steep curve. Curve is known as steep curve. Okay, and the midpoint of this steep curve is known as point of equivalence or equivalence point. So at equivalence point, as we know that the moles of ammonia added will be equal to the moles of HCl present in the analyte. So at the equivalence point, there will be equal number of moles of ammonia added and the moles of HCl in the analyte. Now the hydronium ions are completely neutralized by the ammonia. But again, what is the difference? Since the graph is exactly the same as that of strong acid and strong base, what is the difference between the what is the difference of titration of a strong acid with a weak base compared to the previous two titrations? The difference is, in case of weak base versus strong acid titration, again the pH is not neutral at the equivalence point, as we have seen in the previous case of the titration of a weak acid with a strong base. The point at the point of equivalence, the pH was not neutral, it was slightly basic. Because of this acetate ions produced, acetate ions had combined with water to form acetic acid and OH negative ions. The OH negative ions had made the solution basic. Similarly, here also the pH will be not neutral at the equivalence point. The solution here at the equivalence point will be acidic in nature. The solution will be acidic in nature. Approximately the pH is will range from 5 to 5.5. Let us explain what is the reason behind this. At the equivalence point, the solution, we have seen that what happens, ammonia molecules react with hydronium ion to form ammonium ion and water. So what happens at equivalence point? The solution has only ammonium ions, that is NH4 positive ions and chloride ions. But again, we know that ammonium ion is the conjugate acid of the weak base. So it is the conjugate acid of the weak base. When it will be dissolved in water, it will result into the formation of proton. It is going to release protons into the aqueous medium, and because of the release of protons, our solution becomes acidic in nature. So because of the formation of ammonium ions at the equivalence point, we observe that the solution becomes acidic in nature at the equivalence point. So this was the difference between the equivalence point pH in case of titration of a strong acid with a weak base. In case of the titration of a strong acid with a weak base, at equivalence point we have pH little acidic, whereas in case of strong acid versus strong acid, it was the pH was exactly neutral at the equivalence point. In case of titration of a weak acid with a strong base, the pH was basic because of the OH negative ions produced. Now, in the case of the titration of a strong acid with a weak base, the pH is low because of the production of hydronium ions by ammonium ions. The fourth point is the point after the equivalence point. On the further addition of ammonium ion, we observe that the pH is going to increase because all the H positive ions which were present in the analyte have been neutralized, they have been neutralized by the ammonia molecules added. Now the addition of further ammonia is going to increase the pH of the solution beyond 7. So this is the graph which we get after pH 4. It is exactly the same as that we got in the previous two cases. So let us compare this graph with the graph which we got in the case of the titration of a strong acid with a strong base. So we can see that here the lower portion is exactly the same in case of strong acid and weak base, and strong acid versus strong base. The lower portion of the curve is exactly the same. The difference lies in the upper portion. Since we are dealing here with titration of a strong acid with the weak base, the addition of the weak base is not going to increase the pH of the solution to that extent, whereas the pH of the solution was increased to much more extent when we used a strong base, because we know that the strong base is going to release OH negative ions more rapidly. It will behave as a stronger base. So this is the difference which is observed as compare in the two cases. The upper curve will be the upper curve will be different in the two cases. Okay, the last type of titration is the titration of a weak base with the weak acid. Now, both acid and base taken will be weak here. And suppose we take the analyte ammonia and the titrant is taken to be acetic acid. Now, since again on the x-axis we will be taking the volume of the titrant added, and on the y-axis we will be taking the pH of the analyte solution. As the volume of the titrant, that is acetic acid, is increasing, acetic acid is going to lower down the pH of the solution. So with the addition of titrant, that is acetic acid, in this case the pH is going to decrease, and it is going to decrease. The midpoint of the curve, the midpoint of this curve is known as point of equivalence. The midpoint of the curve is known as point of equivalence. Since in the case of titration of a weak acid with a weak base, no sudden pH change has been observed. Since no sudden pH range has been observed, so we can say that the point of equivalence cannot be studied up to that mark. Okay, so hence the titration of weak base and weak acid are not studied, because the sharp point, the point of equivalence, is not sharp, and hence the titration of weak acid with a weak base is not studied, is not performed. If this is what I said you, if we notice that there isn't any steep bit in this plot, we cannot observe any steep curve. There is just what we call a point of inflection. Only a slight point of inflection is observed here at the equivalence point. Because of the lack of any steep change, any sudden change in the pH throughout the titration, these titrations are very difficult, and we cannot get more information from this curve. Okay, so not much information can be obtained from these curves. So we will summarize now all the titrations which we have studied so far. In the acid-base titrations, a known volume of either acid or base is placed in the conical flask. So in the acid-base titrations, any sample, be it acid or a base, whose concentration is to be known, whose concentration is unknown to us, is taken in the conical flask. And the second reagent whose concentration is known to us, that is a standard solution, is placed in the burette. After the addition of indicator into the conical flask, the reagent from burette is added slowly to the reagent in the conical flask, and the curve of the volume of titrant added versus the pH of the solution is plotted. This curve is known as titration curve showing the change in the pH of the solution in the conical flask, and the reagent added in the burette is drawn. The titration curve can be used to determine the most important, the point of equivalence, the equivalence point of the acid-base titration. It is a particular point at which the amount of acid and that of base are just sufficient. They are sufficient to completely neutralize one another. So from the curves, from the acid-base titration curves, we can come to know about the equivalence point, the particular point at which the amount of acid and bases are completely equal. They are equal to each other. Second important thing which we can determine from the titration curve is that the pH of the solution at the equivalence point is dependent on the strength of the acid and strength of the base tube. So another important information which we have got from the titration curves is that the pH of the solution at the equivalence point is completely dependent on the strength of the acid or base which we are using. For example, if we are using strong acid and strong base, the pH will be same. The pH will be 7. Whereas if you are using weak acid and a strong base titration. When you're performing weak acid strong base titration, the strong, because of the presence of strong base, your pH is going to be greater than 7. So we can say that the pH of the solution at the equivalence point is completely dependent on the strength of the acid and strength of the acid and the strength of the base which we are using. The third point is, when we are performing the titration of strong acid and a weak base, the pH at the equivalence point will be low, because since we are using a strong acid, the pH will be low at the equivalence point. So this was all about different types of titrations. We will just once go through different types of titrations once again. So there are four types of acid base titrations. Acid base titrations are also known as neutralization reactions. In acid base titrations, acid neutralizes base completely to form salt and water. There are of further four types, that is strong acid versus strong base, second is weak acid versus strong base, and the third one is strong acid versus weak base, and the last one is weak base versus weak acid. So we have plotted one by one different curves of all these titrations. The shape of the curve was same in the first three cases, but there was difference in the point of equivalence. The pH was different at for the different titrations. In case of strong acid and in case of the titration of a strong acid with a strong base, the pH was neutral, whereas in case of titration of a weak acid with a strong base, the pH was more than 7 at the equivalence point, and in the third case, for the titration of a strong acid with a weak base, at the equivalence point, the pH was acid. It was low. It was below 7. It was on the acidic portion side. And there are few questions which we will be discussing. The first question is, define titrant and analyte. Analyte is the substance whose concentration is to be determined. So it is the unknown sample which is taken in the conical flask whose concentration is to be determined. And titrant is the solution, is the substance which we take in the burette whose concentration is known to us and it behaves as a standard solution. And the next question is, what are the various types of acid base titrations? There are four types of acid base titrations. And the next question is, discuss in detail titration of a strong acid versus a strong base. And we have discussed the titration by plotting the graph between the volume of titrant added and the pH of the solution. And we have discussed the various 4 points in that. The first point was when no base was added. Second point was the point just before the equivalence point is observed, and the third point was point of equivalence, and the fourth point was the point after the equivalence point. And what are neutralization curves? They are the curves which we get while performing the acid base titrations. And what were its significance? Its significance was, first significance was that it helps us to find the point of equivalence. What is the point of equivalence? How much acid, or what is the basic okay, and how much acid or basic content we have in an acid or a base. And so this is all for this lecture.